Hey guys, it's Miss Manili, and I'm going to give you a quick run through of our first section of Chapter 11. And we're kind of switching things up. Instead of talking about looking at samples and only looking at maybe one measure of either the mean or a proportion, or comparing two different groups in terms of their mean or proportion, we're going to be looking at categorical data. So instead of looking at a mean, we're going to be looking at counts of on several different categories of a variable. So for example, M&Ms, if I'm interested in looking at the distribution of colors of M&Ms, we've done an example, and when I introduce the chapter, hopefully it'll kind of ring a bell. If I just wanted to look at the proportion of blue M&Ms, I could do a one sample z-test for proportions. But if I wanted to look at how all of the colors of M&Ms are distributed, I need to use a different type of test. And the chi-square test is one way that we can do that. And we use the chi-square distributions when we're dealing with categorical data, and not just situations where we have success and failure, but where we have multiple values for our variable. Okay, so we're going to start. We've actually already done those problems. Like I said, we're going to be looking at hypotheses tests. We're going to be looking at distributions of data. We're going to compute what is now the new test statistic, which is called the chi-square test statistic. We're going to be continuing with degrees of freedom, but our formulas are going to look a little bit different. The nice thing about chi-squared is that you won't have to do any confidence intervals. So actually, I think some students actually prefer the chi-square distribution and chi-square test to other types of tests that we do. So as an introduction, sometimes we want to examine the distribution of a single categorical variable in a population. And the chi-square goodness of fit test allows us to determine whether a hypothesized distribution seems valid. So again, like colors of M&Ms. Or if I wanted to look at, for instance, like the distribution of socioeconomic groups in a population, I can use the chi-square test of goodness and fit. If we want to decide whether the distribution of a categorical variable differs for two or more populations or treatments, I could use what is called the chi-square test for homogeneity, and we often organize our data in a two-way table that way. It's also possible to use the information in a two-way table to study the relationship between two categorical variables. So if I was looking at gender over test scores, I could actually compare two variables with different values to determine if there's an association between them. These last two tests, or these last two scenarios, both involve two-way tables, and we're going to get to them in the next lesson. In today's lesson, we're just going to be looking at a single distribution. And so most of what we're going to see, we're going to be able to compute in a list on our calculator. So let's take a look at an example. So Mars Incorporated makes milk chocolate candies. Here's what the company's Consumer Affairs Department says about the color distribution of its M&M milk chocolate candies. On average, the new mix of colors of M&M's milk chocolate candies will contain 13% each of browns and reds, 14% yellows, 16% greens, 20% orange, and 24% blue. The one-way table, or the list, basically summarizes the data from a sample bag of M&M's milk chocolate candies. In general, one-way tables, or again, we refer to them as lists on our calculator, display the distribution of a categorical variable for the individuals in the sample. So it's one variable with several different categories, and we're looking at one group. And so you can see that the values of these of the M&Ms are a little bit different. So we did an experiment like this earlier. If I was interested in the sample proportion of blue M&Ms, I can tell if you add up all of the M&Ms, there were 60 in the bag. Since 9 of them are blue, that means that we have 15% blue M&Ms. Well, if I know that the proportion is supposed to be 24%, I might suspect that I'm not getting enough blues. And if you remember, we did a situation like this in class. When we were looking at confidence intervals, I believe, we were looking at the proportion of blue M&Ms in the bag and trying to estimate it. So if I'm concerned that I'm not getting enough blues, I might think about doing a hypothesis test. So since the company claims that 24% of its M&Ms are supposed to be blue, we might believe that something fishy is going on. So in a previous activities we actually did this using a confidence interval, but we could also do this using a z-test for proportions. And again, it's just a one sample situation where I'd only be looking at the proportion of blue M&Ms. I'd be ignoring all of the other colors. So a success in this case would be blue, a failure would be all of the other colors. And I could do a one proportion or a one sample z-test for proportions to determine if the proportion that I'm getting in my bag is different from what M&M claims. But if I wanted to know about the other colors, if I wanted to know if the proportion of greens was the way it was supposed to be, or the proportion of yellow, if I wanted to test all of the different colors, the other option would be to do a one proportion z-test for each color individually. So that means I would have to run, let's see, 1, 2, 3, 4, 5. I'd have to run 6 different tests to see if I had a significant result or a significant difference for each color, which would really be a pain in the butt. You obviously know how long these tests take to conduct. So that would be a really inefficient method to do. The nice thing about the chi-squared tests is that we can actually assess the relationship with all of the colors at one time. So performing a one sample z-test for each color wouldn't tell us how likely it is to get a random sample of 60 candies with a color distribution that differs as much as the one claimed by the company as the bag that we got. So for that, we need a new kind of significance test. And like I said, this is called the chi-squared test for goodness of fit. Okay, so let's talk about actually the process of going through this type of test. When you're stating your hypotheses this time, instead of using symbols, we actually just use words. And it's actually a lot easier to use words in this case. So the null hypothesis and a chi-squared goodness of fit test should state a claim about the population distribution of a single categorical variable. So for example, my null hypothesis would be the company's stated color distribution for M&M's milk chocolate candies is correct. All right, the alternative would be that I think there's something wrong. So my alternative hypothesis, again, I'm going to state in words that the company's stated color distribution for M&M's milk chocolate candies is not correct. And so instead of using symbols, I'm using words. You certainly could list all of your proportions if you would prefer. So you could have like the proportion of, blue is equal to 0.24. And then down here, you would say the proportion of blue is not equal to 0.24. And we'd be looking at like an OR situation where you'd have to list all of the proportions in your alternative hypothesis. So like I said, it's so much easier just to write it in words. All right. We have to compute a test statistic. So, and actually, here's the difference if you wanted to write it all the way out. But like I said, it's not very efficient to write it this way. So I'd have my stated distribution by what the Mars Corporation claims that their distribution is, and then my alternative would be that at least one of those is incorrect. And notice that the subscript that I'm using is going to correspond to the proportion or the true population proportion of the milk chocolate candies. Okay, so to calculate what we call the chi-square test statistics. So far we've used z-test statistics, we've used t-test statistics, and we had a different distribution. So when you saw a z-test statistic or a z-statistic, you knew to use a standard normal distribution. We know that when you see a z, that corresponds to a normal distribution with a mean of 0 and a standard deviation of 1. When you see a t-statistic, that reminds us that we're using a t-distribution, and the parameter with the t-distribution would be the degrees of freedom. And as you've seen, the degrees of freedom can be computed several different ways. And with the chi-square tests, you'll see degrees of freedom is going to be computed differently as well. So the idea of the chi-square goodness of fit test is that we compare the observed counts from our sample with the counts that we would expect if the null hypothesis is true. And the more the observed counts differ from the expected counts, the more evidence we have against the null hypothesis. The one thing I do want to emphasize is that we're looking at counts, not proportions. So if you think about when we've done the tests of significance on the calculator, for proportions, how you're always entering in an x value instead of p hat, we're always looking at the counts, the observed counts that we would expect versus what we observe. Okay? And so let's talk about how we would do this, because I'm actually going to go through the process with you, and then we're going to come back and talk about the assumptions that need, or the conditions that need to be met and actually carry out the test. So basically, we have this claim from the population that 24% of the M&Ms are blue, 20% are orange, 16 are green, and so forth. What I observed, if you look back at your table, was that 9 were blue, 8 were orange, 12 were green, 15 were yellow, 10 were red, and 6 were brown. So this is a 15. Okay? I need to figure out the expected counts. So there were 60 M&Ms in my bag. So to figure out the expected number of blue M&Ms, I'd need to take 24% of 60. Okay, and so if I were to do 24% of 60.24 times 60, I'm going to get 14.4. Okay, so what I'm going to actually do is put this information into lists on my calculator. So I'm going to put all of my observed counts into list 1 and all of my expected counts into list 2. Okay, and so if I go into stat, edit, I've already put them in here. When it comes to the expected counts, so for example, like in that first category where I'm looking at the expected number of blue, you can actually do the math right in the cell. So I can also do 0.24 times 60 right in the cell, and it'll compute that expected count for me. And so we know that if I take 20% of 60, that's going to be 12. If I take 16% of 60, I'm going to get 9.6. 14% of 60 is 8.4. 13 is 7.8. And 7.8. Okay. And so if I compare these values, I can see that there are definitely some differences, right? I can see that obviously there's a big difference between what I should expect to see in terms of the blue M&Ms and what I actually saw. There's a big difference between the orange M&Ms as well. In fact, the smallest difference appears to be in the brown M&Ms, but there does appear to be, even in like the yellow M&Ms, I observed 15 when I should have only seen about 8.4. So there do appear to be some pretty big differences. The question then is, are those differences significant? Obviously, I know every bag of M&M is going to have a different number of orange, yellow, green, blue M&Ms. But how do I know if those differences are significant? So again, we could do 6 separate tests of one sample proportions, or I can do what is called the chi-squared test for goodness of fit. So this isn't on your paper, but this is just a graph of what it looks like. So you can see the purple bars represent what we observed in our sample. The red bars are what we would have expected to see. Now, if there was really no difference between the two, those bars for each color would be about the same height. And so we can clearly see that there's a difference here. So if we want to answer the question, like, is this difference significant, then we have to calculate a statistic that measures how far apart the observed and the expected counts are. The statistic we use to make that comparison is what we call the chi-squared statistic. And chi-squared, this is actually a Greek letter, and it looks like a cursive X. And so oftentimes you'll see chi-square look like that. So the chi-squared test statistic, this would be another way to write it. And for those of you that have taken AP Bio, I believe that you guys do talk about the chi-squared distribution. Okay, so let's talk about how we actually compute it, because we need to take into consideration each different color and compare the observed to the expected counts. And the way we calculate this is to take the sum of basically the observed counts minus the expected counts. We're going to square it. And remember, we've done this process before. We square it because we know some of those differences are going to be negative and some of them are going to be positive. So we square those values, and then we're actually going to divide by what we expect to see and then take the sum. So this is actually an operation that we can do in our lists. Okay, so we're going to need to do it one step at a time. And notice the instructions are on your paper. So I already have in list 1, those are my observed counts. These are my observed. In list 2, we have what we expect to see. And then in list 3, I want to enter, so we're going to go to the tip top of list 3. In parentheses, I want to do my observed minus expected. Now, I want you to think about any time we're standardizing anything. When we standardize for Z, remember, don't we take our observation minus the mean and divide by the standard deviation? We're essentially doing that to compute chi-squared. Or it's always our observation minus the mean, which remember, we call that our expected value. So I'm going to do list 1 minus list 2. And I need to square that, so I'm going to close my parentheses and square it. And then I also want to divide by list 2. And when I press enter, I should get a bunch of crazy numbers. Okay. And one of the things you might want to get in the habit of doing is just jotting down those numbers. Like if you go back over to your original list here, you could have all of these are your elements of chi-squared. And so then you can just jot them down. So 2.025, 1.333, 0.6, and so forth. And just jot them down so you have them. Okay. Okay. And then once you have all those values, you want to take the sum of list 3. And we're going to do this on our home screen. And to get to that command, we're going to go to second list or second stat, scoot over to math, and then you'll see that option 5 is your sum. And so we're going to take the sum of list 3. And when we do that, that is going to be our chi-squared test statistic. So we know now that chi-squared is equal to 10.1799, which actually is going to round to 10.18. So this chi-square value is very similar to T or Z. It's a standardized statistic that accounts for all of those differences in the counts. Okay? So we're actually kind of going in a reverse order. Normally, before you do a chi-square test, you'd want to check your conditions. But when it comes to chi-square, because one of your conditions is to actually check your expected values, sometimes it makes more sense to calculate chi-squared and then go back and verify that you're allowed to do that. I'm not going to go through that slide. All right, so the assumptions for inference are essentially the same as they've been. We have to have a random data. It either has to come from a randomized experiment or from a random sample. Our population, that 10% condition, we have to make sure that the population is at least 10N when we're sampling without replacement. But notice our large counts. Obviously, we're dealing with categorical data just like we were with proportions. And remember, with proportions, all of our successes and failures had to be greater than 10. Well, with the large counts criteria for the chi-squared, we're looking at the expected counts only being greater than 5. So this condition is a little bit different. We're also not interested in a normal condition here. We're not worried about whether or not the distribution is normal because we are definitely dealing with categorical data, which will never, which is not going to be really associated with a normal distribution. So before we start using the chi-squared goodness of fit test, we have 2 important cautions to offer. The chi-squared test statistic compares observed and expected counts. Do not try to perform calculations with the observed or expected proportions. So it's important that you're dealing with whole numbers and not decimal count or proportions. When checking the large sample size condition, be sure to examine the expected counts. So this is often something that you have to compute. And so you want to make sure that all of those values are more than 5. And remember, when we were dealing with tests for proportions, we were able to look at what we saw in our sample as being successes and failures. But when we're doing chi-squared, you have to look at your expected counts. Okay, so let's just double check to make sure that those conditions are met. If we assume that a bag of M&Ms is a random sample from the population, we certainly know that we're going to have more than 600 M&Ms in our population. And if I go back to my list, I can see very clearly, if I look at list 2, those are my expected counts. All of those counts are greater than 5. So my conditions are met, and it's appropriate to perform this test. So the next step would be to state the probability distribution or the inference method. The sampling distribution, so let's talk about that probability distribution for chi-squared. So far, we've talked about a normal distribution, which we know is bell-shaped and symmetric, and the t-distribution, which is also bell-shaped and symmetric, and actually is going to become closer to normal as our sample size increases. The chi-squared statistic is definitely not normal. In fact, it is always skewed to the right. And it only allows positive values for chi-squared. If you think about it, in our computation where we were doing list 1 minus list 2, or the observed minus the expected, as soon as we square all those numbers, we know that chi-squared is always going to be positive. So you should never have a negative value of chi-squared. When the expected counts are all at least 5, the sampling distribution of the chi-squared statistic is going to be close to a chi-squared distribution. And notice that the degrees of freedom are equal to the number of categories minus 1, not the number of M&Ms. So remember, we were using n minus 1. This time, the degrees of freedom are computed by the number of categories minus 1. And so since we had, I think there were 6 categories with the different colors, so our degrees of freedom in this case would be 5. Okay? Okay. And so this is just some images of what the chi-square distribution looks like. So you can see the chi-square distributions that have like a degrees of freedom of 1 are definitely, they look kind of funky. And as our degrees of freedom increase, you can start to see that the distribution becomes a little bit more bell-shaped and symmetric. So the chi-square distributions are a family of distributions that take on only positive values and are always skewed to the right. A particular chi-square distribution is specified by giving its degrees of freedom. So if I wanted to say like a variable, well, it's not going to be a single variable, but I would just say basically the chi-square distribution with the degrees of freedom would be how you would identify it. But it's not a single variable, so you actually won't probably see that notation anywhere, but that's how you would do it. All right, so if I want to figure out my p-value now, I've got to figure out the probability that the chi-squared value that I got was more extreme. What's the likelihood of seeing that result? So what I'd want to do is find the probability that chi-squared is greater than or equal to 10.177, oops, 17, I think I just rounded it to 0.18. Okay, and we already said that the degrees of freedom in this case, since I had 6 different colors, the degrees of freedom would be 5. So I'm just going to go, we've done this before, I'm going to go to my distribution menu. And now if you scroll down, you'll start to see option 7 is a chi-square PDF. Option 8 is a chi-square CDF, and that's the one we want to choose. This is a continuous distribution. So I'm going to choose the chi-squared CDF. And just like with my other continuous distributions, I'm going to enter a lower bound and an upper bound. If you have one of the older calculators, you might not see it this way. You'd see it as a strand where you're going to have chi-squared CDF, and then you have to know what to put in. Just like with the normal distribution, we'll enter our lower bound, which is going to be that 10.18. And our upper bound, which is going to be 99999. And our degrees of freedom, which we calculated to be 5. And then we'll paste it. And you'll see, whoops, I did it in the wrong spot. Let's go back on my home screen, sorry. Okay, sorry. Okay, so you'll see, if I scroll back, this is what, if you have an older calculator, this is what it's actually going to look like for you. Okay, so you'll have the chi-squared CDF, you'll have your lower bound 10.18, your upper bound of 9999999. Make sure you're putting it in as a whole number and not 0.9999. And then you'll enter in your degrees of freedom and press enter. And so we get a probability of 0.070, which is just 0.07. Okay. The nice thing about chi-squared is you don't have like a sample value and then a test statistic. This is all you have to do in the do part of your test, is just identify the probability that chi-squared is greater than or equal to some number, and then identify your p-value. It will always be greater than. It'll always, always, always be greater than, because we're looking at a value as extreme as the one we got. Since our values are always positive, it's going to be greater than. And so then obviously you're going to interpret that p-value the way we always have. 7% is high compared to our traditional significance level of 5%. So I would say there is not enough evidence to reject the null hypothesis. So let's write it out. So since p is equal to 0.07 and that's greater than an alpha of 0.05, the result is not significant. We cannot reject the null hypothesis. We do not have evidence to conclude. And let's just refer back to what we said the null hypothesis was. Okay, the null hypothesis, in words, I think makes a little bit more sense, that the company's stated color distribution for M&Ms is correct. Our alternative was that it wasn't correct. So obviously, if my result is not significant, I can't conclude, whoops, that the company's claim is not correct or that the distribution is not correct. Okay. And that's how you'd interpret it. All right, so I want to do one more with you, and then there are a couple examples for you to do on your own. So in the next problem, it says genetic research indicates that the following proportions and colors of flowers should occur when cross-pollinating two species of the same flowering shrub. So it says that this is given to you in terms of a ratio, which is a little bit different than the last problem we saw, but it said the ratio of red to pink to white should be 2 to 5 to 1. And a random sample of 50 of the flowers contain the following frequencies. So we had 7 pink, 33, I'm sorry, 7 red, 33 pink, and 10 white. So in terms of proportions, so if you think about this ratio, 2 to 5 to 1, if we think of that as a total out of 8, so the proportion of red should be 2 out of 8. The proportion of pink should be 5 out of 8. And the proportion of white, notice that I'm not putting a hat. The proportion of white should be 1 over 8. And if I just wanted to look at the reds, then I could do a 1 sample test for proportions. But in this case, I want to look at the distribution of all of the colors. So what I have here, this is what I observed. This is my observed data. So this is what I want to put in list 1. So I'm going to go ahead back into my lists. I'm going to clear out what I've got in there. And I'm just going to go ahead, since I'm going to have to use all 3 of these lists, I'm going to go ahead and clear out all of them. And so what I observed was 7 red, 33 pink, and 10 white. Okay. To do my expected counts, well, I would expect in a sample of 50, so here's my sample of 50, I would expect 2/8 of 50 to be red. And so I'm just going to do that on my calculator. 2/8 times 50. I would expect 5/8 times 50 to be pink. And I would expect 1/8 of 50 to be white. Okay. And I'm sort of jumping the gun. But it says you want to determine if these results are consistent with the research findings at the 5% significance level. So actually, let's go in the proper order. The very first thing you want to do is state your hypotheses. And so we can say that we're assuming for our null hypothesis that the research findings regarding the color distribution of flowers. And notice that I'm referring to the distribution of colors, not just the colors, but I'm referring, with the chi-squared test of goodness of fit, I'm looking at an entire distribution of color. So you want to make sure, just like it was really important to include the word mean or proportion in your definitions, it's a good idea to just make sure you're reiterating that we're looking at a color distribution, a distribution of values. Okay. So that would be my null hypothesis, that the research findings regarding the color distribution of flowers is correct. My alternative then would be that the research findings regarding the color distribution of flowers is not correct. So I'm going to do my little cheat thing here. And, oops. I'm going to clone that. Of course not. Oh well. I'm going to have to write it out. All right, so the categories, in this case, we had red, and then we had pink, and then we had white. And it doesn't matter what order you put them in, you just want to make sure that your observed and expected counts are consistent. So I've already kind of filled this information in. So we said our observed counts were 7, 33, and 10, and we know the total was 50. And my expected counts, again, we've already done those computations. I'm assuming that 2/8 times 50, that's my expected count, gives me 12.5. If I did 5/8 times 50, that gives me 31.25. And 1/8 times 50 gives me 6.25. And again, if you add up all those numbers, you should get 50. The next step is to compute chi-squared. And again, we do this by taking L1 minus L2 and squaring it and dividing by L2. So it's always the observed minus the expected squared divided by the expected. So I'm going to do this in my list. L1 minus L2, close the parentheses and square it, and then divide by L2. Okay, and this is a nice small data set, so there's not a ton to write here. I do recommend always writing your expected counts and always writing your chi-square values. If you have a ton of values, I still recommend writing them all down. I know it's tedious. And the next thing we'd want to do is take the sum. So I'm going to do this on my home screen. So if I go to second list, over to math, I'm going to take the sum of list 3. And I get 4.768. Okay, so I did all this work, and I haven't checked my conditions yet. But because one of my conditions is to look at my expected counts, I think that going in this order makes the most sense. But we do need to make sure that all of our conditions for inference are met. So remember, we need to have a simple random sample, and I believe it says in the problem that we have a random sample of 50 flowers, so we know that condition is met. Okay. We can assume the population of flowers is more than 50 times 10, or 500 flowers. And because you have written on your paper, and you should have always write this on your paper, so always write as part of your response. I think you can get away without these numbers, but you always need to include your expected counts because that's one of the conditions you have to check. So the other thing would be to say that all expected counts are greater than or equal to 5. Okay. So now we need to state the probability distribution or inference method. We are using a chi-squared test for goodness of fit. And there are 3 different tests that we're ultimately going to be doing, and it's going to be important to differentiate between them. But the goodness of fit test we use when we have one list or a one-way table. So we have one distribution that has several different variables, or several different values. I'm sorry, one variable, different values. Okay, so that's when we name the method. And the degrees of freedom in this case, we had 3 categories of flowers minus 1, mean that we're dealing with the degrees of freedom of 2. So now what I want to do is find the probability that the chi-squared value that I got is greater than or equal to, and if we look back in our table, it was 4.768. Okay. And I'm just going to go to second distribution. I'm going to scroll down to option 8. Oops, went a little too far. And my lower bound this time is going to be 4.768. And then my upper bound is 99999. The degrees of freedom this time I have to change to 2. And I can paste that. And my p-value is 0.092. Okay, so that's my p-value. And then we want to go ahead and determine whether or not that gives us evidence that our claim is false. And because our p-value is greater than 5%, we cannot reject the null hypothesis because our result is not significant. So we can't conclude that the results are not the same as the research findings. So we can't conclude that there's a difference. Okay. I do want to kind of show you, some of you, if you have a new TI-84 Plus, if you go into your test menu and scroll down past your Z and intervals, you should see a chi-square test, a chi-square GOF test, and then you'll see some other tests that actually we're not going to use an F test in this class. But if you look at those two options, you'll see you have a chi-square test and a chi-square GOF test. Some of you may not have that GOF test option. If you have a TI-84 and you would like me to upgrade your calculator or operating system, I can do that for you so that you have that option. But there is a way to do that's a goodness of fit test. There is a way to do the goodness of fit test using the same methods for inference that we were using with means and proportions. You basically go into that option. You still have to compute your observed and your expected counts in lists, so you still have to do that process, but instead of like doing the chi-squared CDF, you can just tell the calculator where your observed and expected data is. So it should be in list 1 and list 2. You have to specify the degrees of freedom. So this really doesn't save you too much work, but if you do have this option, it's consistent with the other methods that we've used. And so you can get your chi-squared test statistic is 4.768, and the p-value is your 0.092. So it is a little bit faster if you have this option on the calculator, but it doesn't save you that much time. You'll see that this line that's listed, the CNTRB, those are all the values that make up, so let me go back in here. If you look at those numbers, you'll see the 2.42. These are all of the chi-squared elements, the elements that add up to give you your chi-squared value. So if you did want to do this using this option on your calculator, and you wanted to write down all those numbers, they're right there on the calculator for you. Okay, there is one more problem number 2, that deals with manufacturers' packs, prizes in a box of cereal. You're given the claim about the population, and again, these are given to you in percentages. And then you're given the actual box where you've selected 1,020 boxes of the product, and you've obtained data. So let me just kind of go back here. So this is the claim about the population. These are your observed counts. So these are going to go in your list 1. But in list 2, when you put your expected values in, you need to make sure that you're not entering them in as percentages. So you'd have to multiply 0.2 times 1,020 to get the expected number of rings that you would expect to see. So what I'd like you to do as your homework is just complete problem number 2 all the way through, and that will be your homework for this evening. And then on Friday, we'll do a couple problems in class. Over spring break, I am going to give you another video to watch just so we don't fall too far behind. I would really like to be finished this course with at least 2 weeks to spare before AP testing begins so that we can really focus on reviewing stuff from the beginning of the school year. So if you could please finish up number 2, and that will be what I score when I check homework, that would be great. Thanks. And obviously, if you have questions, you can come and see me during Build Out Block.